All right. How you guys doing? Good. All right. We're going to pick up today where we left off on membranes. So we talked about this problem. Today we'll pretty much wrap up conversations about membranes. We'll solve a few more problems together. And then from there, we'll get into disinfection. So I'll probably get your next homework assignment posted by today. That'll just basically take us through all of the material that we're going to cover for exam 2. So unlike exam 1 where we had 2 different homeworks, we'll just have one. It'll kind of capture granular, membrane, so both granular and membrane filtration, and then also kind of disinfection processes. So some of that I'll post, you probably won't quite be prepared for yet, but you'll be pretty close. So feel free to navigate that as you see fit. Okay, so we left off last time we had solved this problem. Just wanted to make a little note. It might be worth your time to make sure you can kind of practice by maybe changing that percent removal. You could put it to 100%, you could put it to 5%, and that would be an easy way to adjust this problem, to make it a new one to solve the mass balance and see if that makes sense, see if you can do that. Of course, you can do this with many problems, right? You change something else or change something, say, okay, well, how much volume would I push through to get some number? So it might be something worth your time to kind of change things if you needed some more practice with that. But overall, this was a mass balance problem, right? We had some number of cells and they were going away or not going away. And what's the new volume? What's the new mass per volume, or number per volume in this case? Okay, so moving on from there and kind of building off of that, we can mathematically describe our balance of solutes in a pretty clear manner using a couple tools. And these are fairly straightforward. You will have these on the equation sheet, but largely they're pretty intuitive anyway. So we can say uppercase R would be the fraction rejected. So uppercase for rejected, and we could say the amount of stuff that we're filtering, the solute, in the last example that would be algae cells, the amount of those rejected, or the fraction rejected, would be 1 minus essentially the concentration that's remaining compared to what was in the feed. So that'll be 1 minus the concentration in the permeate divided by the concentration in the feed. Right? So 1 minus that, because the amount that's in the permeate is the amount that escaped. So what didn't escape is the stuff that didn't make it into the permeate, right? So we can understand the fraction in that way. So again, just using the permeate, the feed, retentate, all as our catch terms for where the water is going in our membrane. And if you think back on our last problem, we didn't have a flow rate for the retentate. We just stopped at some point. But this equation can still apply, right? We could go back a step and say, okay, well, what was the concentrate that was in the permeating fluid? And that'll tell us something about what was the concentration in the, that comparison to the feed. Okay, another way we can describe this is just a reformulation of the same concept there. For cases where we want to deal with something like 99.9999% rejection, but that's kind of cumbersome to say. We could say R log. So on a logarithmic scale, we can take the log of CF divided by CP, and we notice that that's kind of a little bit inverted, but taking the log of it will tell us how many orders of magnitude have been rejected, which is kind of what's convenient, right? 2 orders of magnitude would be 99%. 1 order of magnitude would be 90%, and so on. So we can say R log is the log of CF divided by CP, and that makes it so that the R log for a 99.99% removal is a 4 log removal. So the math here is worked out so you can kind of see it very clearly. We could describe just R for that scenario as 1 minus 1 divided by 10,000, which would be 0.9999. Or we could say the R log is 4. So 4 log removal. Okay, like I said, pretty straightforward, fairly intuitive. But I'm going to give you these formula. Just make sure that you understand what the pieces are, right? That's your task essentially, so that you can interpret a problem and solve accordingly. Okay, we can also talk about the water balance. So that's a solute balance. Well, what about the water? A big part of filtration in general is how much of this water can we actually use? What fraction of it or percentage of it is going to become usable clean water that's our target. So we're going to use, and I'm keeping consistent with our book's nomenclature here, a lowercase r. So sorry about all the r's, but lowercase r for water recovery rate. This will be the QP divided by QF. And you can tell it's dealing with water because we're talking about flow rates now instead of the concentrations of something. So QP over QF. QP being the amount permeating, the flow rate, per QF being the flow rate that we're feeding to the membrane in the first place. So QP, if we put these in cubic meters per second, we want both that way. We can also recognize that for a system where we have some membrane like that, we have a QF. We have some permeating flow crossing that membrane. That means we have probably some flow that's not crossing it, Q retentate. Well, we're not creating or destroying any water here, so the Q total is going to be QF. And so we could say QF is equal to QP plus QR. So just to make that note, hopefully that's the obvious once we say it, but if you forget that when we're solving a problem, you might be scrambling to figure out, oh, well, what's this flow rate, right? So just keep that in mind. Water's going somewhere. We have conservation of water here. Okay, so as an example, could just do a real quick with just in our minds here. If we had a membrane system treating 100 liters per minute of water, 15% of it goes to waste, then the water recovery rate should be 85%, right? 15% is going to waste. Water recovery should be 0.85 as a fraction. Okay. Hopefully very straightforward. In that case, that would be, we could even say that's 85 liters per minute for the QP, and then the QR, that's the retentate, would be 15 liters per minute. That's the waste, right? So when we have a membrane treating water and we're using the permeate, then what's wasted would be the retentate. It's collecting the particles. Occasionally we want to collect particles or something for an application, but typically for water treatment we are just discarding that to waste. Okay, makes sense? Pretty straightforward. This stuff is not crazy complicated. Just want to make sure that you know what's happening with these pieces here. Okay, next would be some flux terms. So another concept that we need to be able to use is, well, how much water are we getting per area of our membrane, right? We talked about that already, how it scales typically kind of in a general sense, but how are we going to calculate or identify that given some particular scenario? So J is what we'll use to describe flux, and we'll call that a flux across the membrane. Just like our granular filters, this is a volume of water crossing some surface area. And so it can look like a velocity term through that area, but it's better known as a flow rate per area, right? Q over A. So maybe we'll have it in liters per square meter per hour. We could also have it in cubic meters per square meter per hour, or any such terms. This one, you'll see the meters could cancel and you are left with what looks like a velocity, right? And you could also check the velocity across that membrane, and that would be the same number. Okay. So again, this is one definition of our flux then, the QP divided by AM. And keep in mind that when we are talking about flux that we are producing water, this is flux that crosses that membrane. So that's based on the flow rate of the permeate, not of the flow that we're giving to the membrane. So the giving to the membrane, that's the feed, right? We're shoving a certain amount of water to the membrane. Some amount of that crosses, that's the flux that it has to cross. So we're going to use QP. Crosses the membrane. Okay. We'll have a few other ways to calculate Q given some parameters, maybe pressure and some resistance that the membrane offers. But this one relates it to specifically to the area and the flow rate. So this is a very convenient term when talking about the bigger picture design. So maybe we'll see, okay, well, how much area do we need if we have such and such a membrane and we can only offer it such and such a pressure, right? And then we can figure out how much membrane area we need to supply some demand. Okay, so let's take a look at an example. This is from a supplemental. This is not our book. Our book doesn't have a lot on membrane, so I've grabbed some resources from elsewhere. Happy to share more reading materials if you need, and I might already be on Moodle. So in this case, we have a Dow FilmTech membrane module that contains, so this is going to be one of those hollow fiber membranes that has tons and tons of small fiber membranes. Bunch of small cylinders, basically, is the geometry. Contains 5,760 fibers. The fibers are 1.87 meters long. So fairly long. With an outside diameter of 1.33 millimeters and an inside diameter of 0.7 millimeters. So we're giving outside and inside diameters here. So when we look at the geometry, maybe we need to account for that. Okay, then we are tasked to calculate the water production from one module if the flux is 75 liters per square meter per hour. And the flow direction is either, in the first scenario, going outside in, and the second one, inside out. So number one is outside in, and number two is inside to out. Now what we're referring to with the outside in, inside out, that is referring to the water traveling either to the membrane where it's going to be separated, coming from the inside of the membrane, this tube first, and then escaping out, or we're feeding water outside of it that it's going to push through the barrier and end up on the inside of this tube. So this is just a matter of, are we sending in, we'll say outside in, if we have a tube, the water is coming and making its way inside. Whereas inside out, the water is fed in and making its way out. So what that means is there's a difference in geometry in terms of the surface area for the separation. So the separation is going to occur where the water first meets the membrane. We would generally design a membrane with one or the other in mind for operation. So there's going to be a slight surface area difference because we have this, the length is 1.87 meters, and the diameter here on the inside diameter was 0.7 millimeters, and the outer diameter was 1.3 millimeters. Okay, so I'm going to give you a few minutes to tackle that problem. See if you can solve that. As always, feel free to work together ask me questions, any of that. All right, so hopefully you've had a chance to either get some answers or get close here. So the way to tackle this problem is really to look at the surface area, right? So the surface area of one fiber should be the length of the fiber times the circumference. So 2 pi times the radius is the formula for circumference, right? And so it's be pi times diameter is our circumference. Multiply that by the length of the tube or the fiber, and we'll get an answer over here on the right for the surface area for either the outside or the inner diameter of the hollow fiber. Then we can take that and multiply it by the 5,760 fibers per module to get a total surface area per one module. And that's the value here, about 44 and almost 24 square meters. So based on whether or not we're operating it outside or inside. So we notice here that's actually almost a factor of 2 different, just selecting which way we're arranging this treatment. So from there, we need to take our flux measurement that was given. We know flux is going to be Q permeate over area. And really what we're solving for is we are looking to find the QP, right? The question asked, calculate the water production. That sounds pretty generic, but if you think about it, perhaps we could be talking about a volume of water produced, but that would have to be over some time. And we're not given anything like that, so it should be a flow rate. Water production then should be a flow rate of water produced, meaning that it's passed through that membrane and usable, right? So that's going to be QP that we're looking for. So we want to know QP1 in this case and it doesn't specify the units, but we're given liters per square meter per hour. So I would say let's go ahead and just leave it in liters per hour and solve that way. And we can do the same thing. So that means, to solve that, we would say QP is equal to that flux times the area, right? So we would take 75 times that 44 to get our answer. And I've done this in Excel. So that would be 3299 for this one. So just about 3,300 liters per hour for the first case. You can do the same thing in the second part. Of course, J, by the way, is that 75 liters per square meter per hour. And if you're following the units, you see the meter squared cancel very nicely, and we can just keep with that those units. So we'll call this QP1. Then we solve for QP with a second operation. Same process, and we end up getting 1,777, or 76.5. Liters per hour. Okay, yeah. I think so. Maybe I didn't. So I've got the length there, surface area. Yeah. You getting something different? Yeah, I think the numbers here look like what I've had in the past times that I've solved it. So I think the calculations are correct, but if anybody else has wouldn't be the first time I've made mistakes. So somebody else sees something. Yeah. All right, does that make sense though? Overall, the process for solving these membrane problems, they're never going to be ultra complicated for the level of stuff that we're going to do. They are inherently kind of simple because we don't have reactions happening. At the worst cases, they're fouling some, and the resistance changes, which might change our flux a little bit or change the pressure requirement. But it's relatively straightforward once you get a handle on where the pieces go and what the parameters mean. Okay, so speaking of force then, let's talk a bit about that. We have TMP as the transmembrane pressure. That's the pressure across the membrane. So if we have a pressurized feed, we typically have a pressure drop because it's requiring some pressure. You can think about, when you turn on a faucet, you open it up a little bit, there's only a small amount of pressure coming out. If you open it up all the way, whatever pressure is in the pipe is pretty much the pressure you're getting out, right? So in that sense, you can think of the membrane as some sort of a faucet that is in the faucet case, you have a valve that is letting a certain amount of flow rate and therefore pressure and volume and all that come through. And in the same way, a membrane, based on how big the pores are, will allow or prevent some amount of pressure. So we can push water through a membrane in that manner. And we'll call that pressure difference between the feed and the permeate our transmembrane pressure. Now, in the laboratory, sometimes you'll have a membrane driven by a vacuum. So just a little side note here, the membrane driven by a vacuum can only reach a certain amount of transmembrane pressure because you can only drop a vacuum to 0. And then the driving force is then your atmospheric pressure. So unless you were going to take your apparatus to Mars and then you have a bigger differential between your atmospheric pressure and your vacuum, you're only going to get so much pressure by doing a vacuum-driven membrane. Now, for some cases, that's plenty, right? Some membranes, some operations, a vacuum is a perfectly reasonable way to pressurize your membrane. Other cases, you just have to go higher, and you would have to drive the water at the membrane, pressurizing the water itself. Okay, side note aside, we'll say that we would typically report these in pascals. That's going to be convenient because pascals ultimately are kilograms, meters, and seconds in terms of units. So that's going to be a typical and a convenient way to work with them. If you had to do some unit conversion, I would give you some indication of how to do that. Okay, any non-obvious one, like going from atmospheres to pascals or something like that. Okay, so TMP, that's one pressure minus the other, right? The feed minus the permeate. Another thing we could say is that we can relate this pressure to flux and say the flux is going to be equal to that pressure that we're applying across the membrane divided by a term called membrane resistance, and we'll say total membrane resistance, times, that resistance times viscosity. So it's the transmembrane pressure divided by both of those. So viscosity is, how viscous the water is. That could change a bit with temperature. It would change if we had a different type of liquid. It would be a lot easier to filter air in that sense, given some membrane resistance. But even air, you could feel it's going to have some viscosity. Okay, so this total resistance number, this is going to be in inverse meters. It's almost going to be like a percentage of resistance if you traveled through 1 meter. Now, putting it in meters is kind of weird because most of our membranes are hair thin, right? The actual separation layer is so thin that it's a very, very, very small fraction of a meter that we're actually talking about traversing. So this RT value is going to be a rather big number. It's just going to feel unwieldy large. But since we're working with meters and all the units are going to be meters, it makes sense. It's just going to be a weird large number, right? So I'm just going to make a comment that that's going to be a large number because membranes are much thinner Okay, that's not hugely important. I'm just giving you a warning that we're going to be dealing with membrane resistances like 10 to the 12th meter per meter or something. And it's just going to feel a little weird. But then once you think about it, okay, well, how much resistance is this providing, maybe as a fraction? If we had to push it through 1 full meter, maybe that gives a little more idea. Okay, we've worked with dynamic viscosity before, so there's nothing really new there. And ultimately, it's going to be convenient to put all of these units in meters and seconds. So dynamic viscosity being kilograms, meters, and seconds. Again, transmembrane pressure being in pascals puts it in units of kilograms, meters, and seconds. And so when we put those together, if we put TMP in pascals, the resulting flux would be in meters per second. Quite convenient. Okay, let's talk about that membrane resistance. Yeah?
I was just going to say, shouldn't pascals be kilogram meters per second squared?
Yeah, I wasn't meaning to, and thank you for that, and because honestly I had forgotten the specific, right? You said kilograms per meters per second squared?
Yes.
So I was just meaning that those are the components of it, right? But thank you, that's perfect. So kilograms. So if we then took a look at that and put kilograms per meter per second squared there, and also put in the membranes as per meter and put in the viscosity as kilograms per meter second, all those should come together and give us a flux term. All right. Okay, so let's talk then about what is providing the membrane with some sort of resistance. And really what I'm referring to is the separation layer itself and whatever fouling and stuff that might happen. So here's a few electron micrograms, so scanning electron microscope images from actual membranes. And they look pretty neat if you slice them in half and take a look at a cross-section. You can see that effectively what you have are larger pores to allow water to flow as easily as you can through where you just want a supporting layer. It's almost going to be like a sponge or something. And then at the edge of it, you want a really thin separation layer, the thinnest you can, while also being sturdy, right? You don't want it to break and let larger stuff through. So you want a very porous area through here, and then a very thin and sturdy, supported separation layer. There are so many types of membranes, so many ways to design these. You could look at them, all sorts of membranes, and you'd probably find different architecture or different appearance to them. But any membrane that is finding good use and pretty good efficiency is going to have some type of formulation like this. Here we have another. You can kind of see the separation layer in that area. And everything else down here is sort of the support. So it's a way to kind of hold that separation layer together and allow it to withstand the pressure that's going to be applied to it. Okay, so we see different ones. Even right here is very fine separation layer. It kind of looks like nothing could get through it in some sense, and so on. Now, as soon as you start filtering dirty water, you're going to start accumulating junk, particles. And as you see, these are not ever going to be perfect little particles with perfect little pores that are going to block them or not. So we're going to have some random assortment of where stuff starts accumulating. And we're going to end up having fouling that we see here, right? So accumulation of particles on top of particles will eventually make its own separation layer unless we clean it off. So at some point we could have, and we'll talk about this in a moment, so many particles building up that we could have a cake layer, is what we call it, where the cake is doing filtration that's finer than the membrane itself. So if we leave it going for long enough, we might even improve the removal efficiency in terms of what can we remove, how small of things can we remove, but that's going to be at the cost of higher energy costs because our resistance went up and our flux will go down, or the pressure will go up. So this would be a cake layer, and this is from fouling. So we call it fouling when the membrane gets dirty. We often have lots of procedures, maybe physically cleaning, maybe physically shaking, scouring it with bubbles, backwashing it, eventually dunking it in acid or bleach or something. Lots of ways to try to get rid of that fouling. A lot of times it's going to be just a quick little reversal of our pressure to just backwash it like that, or something like that. So there will often be routine, quick back flushing or vibrational energy, something to try to shake off the dirt during operation and let it go out the retentate. And then maybe after some days or weeks or some amount of time, a more hardcore cleaning for the filter, depending on the application. Okay, so let's talk about that resistance. I already mentioned this cake layer resistance. So if we have a membrane, I'm just going to draw, I'm going to draw one of these membranes where we have small pores at the top, or on the right rather, and larger channels going to try to do kind of a quick drawing here so that you get the picture. So we have a separation layer on the right and just a supporting layer throughout the rest of it. Now we can describe a few different types of fouling or resistance that the membrane can have or exhibit. And so the first thing we could say is the membrane itself is going to have some resistance, right? It's kind of self-explanatory. We've been talking about this. It's hard to push water through one of these membranes. Just clean, perfect, pure membrane, we would have some membrane resistance. So we could identify just by itself, we could have some membrane resistance. So nothing else added, we'll have Rm. And we're just going to sum whatever kind of resistance we have to a total resistance, okay? So it's not going to be super complicated. We're just going to say all the resistance that is there is this RT. That's what we're going to use in our flux equation. But we could then solve a problem to say, oh, we just doubled the resistance by fouling or something, right? Or we added 10 to the 10th resistance for making a fouling cake layer or something. Okay, so if that's just that just the membrane itself could have some fouling, we could also describe foulant resistance, which would be any particles that are kind of accumulating in the pores or somewhere else. So if we start having particles start blocking a little bit on the surface and just throughout, they're kind of sticking to different spots, they're sort of starting to constrict the pore size a bit. This is the generic foulant resistance. So, and there's some fancy terms we could go into all of this, but we'll just say this would be RF for kind of standard fouling. Then if we let it go too long, we'll eventually get to the cake layer formation. And this is when we probably also have the fouling below, but now we also have kind of that cake layer that we talked about. We'll say that's RC. Okay, so we have different sources. We could call it different portions, different types of accumulation of particles contributing to fouling, and all of these would be total fouling, total resistance rather. Okay, and we'll put that in per meter terms and put that into any equation we have for flux. So this means, kind of obvious, why is the filtration important, or the filter cleaning important? Well, because our flux is going to depend on the pressure requirement and the resistance, right? So if we flip back to that equation real quick, if we increase RT, that's going to decrease flux, or it's going to require that we increase our pressure, right? Just directly. So that's the deal. That's also why really fine membranes for removing really, really small stuff, they just inherently have a lot of resistance and therefore require a lot of pressure. And the inverse is true. Also, you tend to get very little flux out of them. So both of those are kind of happening at the same time. A bit of a trade-off there. And part of that trade-off, by the way, is what we make the membranes out of, they can only handle so much pressure. So even if we could pressurize a system really, really strong so that we, to meet the flow rate that we really wanted, chances are the membrane itself can only handle so much. So at some point we have to just settle for less flux. Okay, so a little bit deeper here, we can talk about membrane permeability. This is another associated concept. I'm going to keep this pretty basic. We could go into depth. There's quite a lot of physics and fluid dynamics involved with really charting what's going on with membranes at the pore level. But we could talk about a permeability term, LP, that would just relate also the flux compared to the pressure, right? So we could say permeability is flux over transmembrane pressure. And that's very like saying what we just said. If we notice, previously we had J is equal to TMP over the resistance times the viscosity. So in some sense, what we've done is we've inverted those two pieces. Let's say if we divided both sides by J and then put the resistance and the viscosity on the left side, the resistance and the viscosity are very close to the same thing as the permeability, except inverted, is how that could make sense. So anyway, it's not, we don't need to do a lot with this, just saying that's another way, another term we could use. And we can also look a little further on some of these models showing how the membranes could be fouled in particular. So we already talked about cake filtration, where particles now have to filter through the pores of those other particles or water has to filter through them. And these new pores might be smaller than the pores that were the membrane itself. We could have complete blocking. That's if the particles sit straight into the pore and just plug it up all the way. That's actually not too common. Standard blocking is a little more common, where you just start accumulating the particles along the edges of the pores. And at some point, you're getting somewhere between that standard and cake filtration. Okay, so just a few other things to look at. And I think I've just got problems from here. So let's take a look at this one. I have, pretty sure I've given this one on an exam before, just so you can have a feel for the type of problem we might look at. So here we have operators of a small groundwater cleanup decide to implement cross-flow microfiltration membrane, a cross-flow unit, as a pretreatment step to ensure influent groundwater doesn't contain large particles that can clog other stuff. The system must treat 200 liters per hour. It utilizes a membrane pore size of 2 micrometers and must recover at least 95% of the water. The influent water contains 30 milligrams per liter of particles, and the membrane rejects 85% of those particles. So part A is labeling the diagram. B is then asking what concentration of particles are in the permeate. C, what concentration of particles in the retentate. And then D, if the membrane is rated for a flux of 25 liters per square meter per hour, what total membrane area is required to meet these flow demands. Okay, so I'm going to give you some time. Again, you're welcome to work with your classmates or ask me questions. Merci. Right, so I'm just going to go through parts A and B with you real quick. The Q feed here should be A. Flow B should be the retentate. C or D should be the permeate. Right. We're just looking at what water crosses over that arbitrary line. And for part B, we have the formula that we have some fraction rejected as 1 minus Cp over Cf. We can say that the problem tells us it rejects 85% of particles. That should be our R, right? So 85% divided by 100 to put it into fraction, 0.85. So we can solve, we know that the particle concentration in the feed is 30 milligrams per liter, and we get, therefore, the Cp is equal to 0.15 times Cf. That gives us 4.5 milligrams per liter for the answer to part B. Now, before we move too far ahead, I think you can probably go ahead and solve part C, and I'll give you time to do that next. But looking at the problem and looking ahead at part D, the problem is actually a little bit vague, and unfortunately so. It says the system must treat 200 liters per hour of water, and the context is they're treating groundwater. So they're pulling up groundwater to treat it for cleanup. So it's not like we're producing water to drink. Because if we were producing water to drink, I would for sure think, okay, well, we need 200 liters per hour. That's got to be permeate. But if they're treating that much dirty water, and they just have to pump that much out of the ground every hour, well, that actually might be the feed. So I'm a little ambivalent about which one we call it. I think the problem just should clarify. But for today, let's call that the QF. But there's an important question there, right? Because a lot of times that's going to be QP for producing that much water. So the context here is a little vague, but we're going to say, we'll say QF is 200 liters per hour. Of course, you can solve it either way, right? Your answer would just be a bit different. I mean, if the problem was more clear, it might be incorrect to solve it one particular way. But I'm saying you can find a solution either way you say it. So today, let's just call it that QF. Okay, so I'm going to give you a few more minutes for part C and D then. All right, so hopefully you had a chance to brush up against the problem of, well, how do we find that CR, that concentration of the retentate? Well, we need a few pieces to get there, and that's going to be a simple mass balance on whatever water is going in with some particles is going to ultimately be equivalent to the same amount of particles going out in one way or the other. It's just the membrane is separating which direction they're going, right? So it's a lot like the very first mass balance we solved in this class where we had two streams coming together to make one new concentration. It's just kind of reversed because the membrane can separate the particles that way. So in this sense, we need to find the flow rates for each of them, and you see I did that. We know that the feed we said is 200 liters per hour, and we were given that the recovery rate has to be at least 95%, so I just went ahead and said the recovery is 95%, just to call it that. And then we would say that means if R is QP over QF, that's the percent of water we recover, that means QF should be 190 liters per hour. That leaves 10 remaining, so the Q retentate should be just 10 liters per hour. And presumably this operation has to deal with that as well. It's extra dirty water, and they'll have some way to do that. Okay, so then at that point, we can then pair and make that mass balance of what's going in is equal to what's going out. QF times CF, it's going to be ultimately a concentration per time unit, is equal to what's going in, excuse me, not what's going in. that what's going in is going to be equal to the two terms going out, QP-CP and QR-CR. So with that, the only unknown is CR once we found the Qs, and we can solve that, put in the numbers, 200 liters times 30 milligrams per liter is equal to 190 times 4.5 plus 10 times CR. So we solve that, that should come out to 515-ish milligrams per liter in that retentate feed. So this is a good example of how the membrane problems can be super simple, but also could throw you for a loop if you're not really seeing what you need to piece together here, right? Kind of a common theme here. So just understand that you can probably do it no problem mathematically and all that. It's just a matter of getting the pieces where they need to be. Any questions on that? Does that make sense? Okay. All right. So then the last part says, what is the flux required? Again, this is going to be a little odd because we're defining that 200 liters per hour as the feed. So that means, well, flux, it's flux across the membrane. So to handle that much feed, we're actually only getting 190 liters per hour across the membrane. So then we're going to still use QP over AM as our equation for flux. So we'll set that equal 25 liters equal to QP over AM, put in our numbers and solve for that area, and we need 7.6 square meters of membrane area for that problem. All right, make sense? Okay, and you can imagine we could solve problems with membrane resistance and flux and pressure. It's not going to be a huge amount different, and we could then relate, okay, given some flux that we calculated, you know, what membrane area do we need? Do we need some new membrane area if the resistance increases a certain amount? We can connect a few more pieces there too, but it's not inherently going to be that much different than what we're doing here. All right, that's all I've got for you today. We'll see you on Tuesday.